up at the stars, we've wondered about the origins of the universe. How did everything come into existence? For decades, the Big Bang Theory provided a satisfying answer. This powerful explosion, which took place around 13.8 billion years ago, is thought to have set in motion the expansion of the universe as we know it. But now, with the launch of James Webb, a new frontier in space exploration opened up, and with it, an unsettling glimpse into what may have occurred before the Big Bang itself. The revelations have shaken the scientific community and sparked profound existential questions about the nature of reality and the universe we inhabit. Join us as we dig deep into how James Webb just unlocked the biggest cosmic mystery. For decades, the Big Bang Theory stood as the cornerstone of cosmology, offering a comprehensible narrative of how the universe came into being. According to this theory, about 13.8 billion years ago, the universe began as a singularity, an infinitely dense point that contained all the matter and energy of what would become the universe. This state was unstable, leading to a massive expansion we call the Big Bang. Contrary to popular belief, this wasn't an explosion in space, but rather the rapid expansion of space itself. In the first tiny fraction of a second after the Big Bang, the universe was a seething hot mass of particles and energy. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate. This period is often referred to as cosmic inflation, where the universe expanded exponentially, smoothing out space and setting the stage for galaxies and stars to form. As the universe cooled, particles like quarks and gluons began to form protons and neutrons, which later combined to create atoms. Hydrogen and helium, the lightest elements, emerged about 300,000 years after the Big Bang during a period called recombination, when the universe became transparent to light. The leftover radiation from this event is known as the cosmic microwave background, which we can still detect today. Over the next billions of years, gravity pulled together clouds of hydrogen and helium, forming the first stars and galaxies. Inside stars, nuclear fusion created heavier elements like carbon, oxygen, and iron. When massive stars exploded in supernovae, they scattered these elements across space, seeding future generations of stars, planets, and eventually life as we know it. However, despite its widespread acceptance, the Big Bang Theory has always been haunted by unresolved questions. As told, at the heart of the Big Bang Theory is the concept of a singularity, a point where the laws of physics as we understand them break down. This singularity represents an infinitely small and dense state from which the universe is said to have emerged. However, the idea of a singularity itself presents profound challenges. The notion of infinite density and zero volume defies our conventional understanding of space and time, suggesting that our current physical theories, including general relativity and quantum mechanics, are incomplete. And one of the most tantalizing questions that arise from the Big Bang Theory is what caused the Big Bang? What existed before it? Was there even a before, given that time and space supposedly began at that moment? While these questions have been largely theoretical, recent findings from the James Webb Space Telescope have given us new and deeply disturbing clues. Launched in December 2021, the Webb telescope has been equipped with cutting-edge infrared capabilities, allowing it to peer deeper into the cosmos than any previous telescope. Where the Hubble Space Telescope could only glimpse at faint traces of distant galaxies, James Webb can capture the earliest light emitted by the first stars and galaxies, giving us an unprecedented view into the very fabric of space-time. But Webb's capabilities extend beyond simply observing early galaxies. It can also capture data about the universe's structure, composition, and evolution in ways previously unimaginable. As scientists analyzed the data streaming in from Webb, they began to notice something peculiar, something that didn't fit within the framework of the Big Bang Theory. One of the most stunning discoveries made by James Webb is its detection of structures in the early universe that should not, by all accounts, exist. Observing galaxies that are thought to have formed just a few 100 million years after the Big Bang, astronomers have encountered mature, well-organized galaxies that challenge our understanding of cosmic evolution. These galaxies seem far too old and complex for the timeline provided by the Big Bang model, which suggests that the early universe should have been a chaotic, turbulent place, with galaxies still in their infancy. What's even more alarming is Webb's observation of faint cosmic ripples, traces of energy that seem to date back to a time before the Big Bang. These ripples could be the remnants of a pre-existing universe, something that existed before the event we've come to understand as the beginning of time itself. If this is the case, it suggests that the Big Bang may not have been the true beginning, but rather a transition, a new phase in an eternal cycle of cosmic destruction and rebirth. What's notable, the idea that there might have been something before the Big Bang is not entirely new. Various theoretical models have posited the existence of a multiverse, suggesting that our universe is just one of many universes, each with its own physical laws and properties, in a vast multiverse. In this model, the Big Bang could have been the result of a local event in a larger multiverse, with other universes constantly being born through similar processes. This could involve mechanisms like eternal inflation, where different regions of space experience continuous cosmic inflation, each giving rise to a new universe. The multiverse concept offers the possibility that before the Big Bang, there were other universes or cosmic regions that existed and gave rise to our own. Another theory is the idea of a cyclic universe, where the universe goes through infinite cycles of expansion and contraction. In this model, the universe could have experienced multiple Big Bangs and Big Crunches. After expanding for billions of years, the universe could collapse back into a singularity, the Big Crunch, only for another Big Bang to occur and begin a new cycle. This concept has been explored in various forms, from ancient cosmological ideas to modern versions like conformal cyclic cosmology, proposed by physicist Roger Penrose. However, Webb's data brings a disturbing new dimension to these theories. If the faint cosmic ripples it has detected are indeed traces of a pre-Big Bang universe, then we are faced with a chilling possibility. The universe may be caught in an endless loop of destruction and renewal, where everything that exists is destined to be obliterated, only to be reborn again in a new form. This raises questions about the very nature of existence. Are we living in a universe that is fated to collapse, with all matter, life, and consciousness erased, only to be replaced by something else? The concept of eternal cycles of cosmic death and rebirth may sound philosophical, but Webb's observations lend it a disturbing degree of scientific credibility. We may be part of a universe that is not unique or special, but merely one in an infinite series, with countless others having come before and countless more to follow. The realization that our universe, and by extension, everything within it, is impermanent, subject to a cosmic reset, is nothing short of terrifying. One of the most unsettling aspects of Webb's discoveries is the suggestion that time itself may not be linear. According to our current understanding of physics, time began with the Big Bang. But if there was something before it, what does that say about the nature of time? Some theorists have begun to speculate that time might be cyclical rather than a straight line. In this scenario, the concept of before and after becomes meaningless, and the universe may be in a perpetual state of becoming, constantly evolving through an infinite loop. From the moment we are born, our understanding of reality is deeply intertwined with the flow of time. We sense its passage as a series of events, moving from the past through the present into the future. However, this perception is not necessarily an accurate representation of how the universe operates. In the early 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. He demonstrated that time is not a constant, as Isaac Newton had previously assumed, but is flexible and relative, depending on the observer's velocity and the presence of massive objects. This discovery revealed that time and space are woven together into a four-dimensional fabric known as spacetime. This means that time does not flow uniformly for all observers. A clock on Earth, for example, runs at a slightly different rate than a clock on a satellite in orbit. The faster you travel, the slower time passes relative to someone at rest, a phenomenon known as time dilation. Yet, relativity still treats time as something that exists, even if it is flexible and malleable. More radical ideas suggest that time might not exist at all, at least not in the way we commonly experience it. In quantum mechanics, the very nature of time becomes even more puzzling. Quantum mechanics deals with the behavior of particles at the smallest scales, where the classical rules of physics break down. In this realm, particles can exist in multiple states simultaneously, and their behavior can be described only probabilistically. The concept of time in quantum mechanics is particularly problematic. At the quantum level, time often appears to be irrelevant. When physicists describe systems of particles using equations such as the Schrödinger equation, time is just another variable, treated symmetrically with space. This is in sharp contrast to our everyday experience, where time seems to move in one direction only, from past to future. In quantum mechanics, the fundamental laws of physics are time reversible, meaning that they do not distinguish between past and future. This suggests that time's arrow, the irreversible flow of time that we experience, might not be a fundamental feature of reality, but instead an emergent property. The concept of time in quantum mechanics becomes even more complicated when we consider entanglement, a phenomenon in which two or more particles become linked in such a way that the state of one particle is instantaneously correlated with the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our understanding of both time and space. In entangled systems, the flow of time seems to become irrelevant. The relationship between particles does not depend on a linear sequence of events, suggesting that time might be less fundamental than previously thought. One of the most intriguing theories that challenges our conventional understanding of time is the block universe theory, also known as eternalism. This idea arises from Einstein's theory of relativity and suggests that time is not something that flows, but rather a dimension in which all events, past, present, and future, coexist simultaneously. In the block universe, the passage of time is an illusion created by our limited perspective. Imagine time as a landscape. When we stand at one point on this landscape, we experience that moment as the present. However, from a higher dimensional viewpoint, the entire landscape, the past, present, and future, is laid out all at once. Just as all points in space exist simultaneously, all points in time exist simultaneously. The past is not gone, and the future is not yet to come. They are simply parts of the space-time continuum, existing as part of a larger, unchanging whole. If the block universe is correct, then time does not flow in the way we perceive it. Our experience of time might be similar to watching a movie. We see the frames one after another and perceive motion, but in reality, the entire film exists at once. Our consciousness might be moving through time in a similar way, experiencing moments sequentially, even though they all coexist in the space-time block. Despite these radical ideas about time, we still experience the world as a sequence of events. A glass shatters, but it does not spontaneously reassemble. Ice melts, but does not freeze on its own. This irreversibility of time, the so-called arrow of time, is deeply rooted in the laws of thermodynamics, particularly the second law, which states that entropy, a measure of disorder, in a closed system always increases over time. Entropy provides a direction to time that seems absent in the fundamental laws of physics. While the equations governing the universe at a microscopic level are time-reversible, meaning they could work equally well if time ran backward, the second law of thermodynamics introduces a preferred direction, from lower entropy to higher entropy. This gives rise to the arrow of time that we experience. However, some physicists argue that the arrow of time may itself be an emergent phenomenon, rather than a fundamental aspect of the universe. It could arise from the initial conditions of the universe, particularly the extraordinarily low entropy state at the moment of the Big Bang. If this is the case, then the arrow of time might be a consequence of the universe's birth rather than a fundamental feature of reality. This again raises the possibility that time, as we experience it, is not fundamental, but rather a product of the specific conditions of our universe. Philosophically, the notion that time may be an illusion has profound implications for our understanding of consciousness and existence. If time does not exist as we perceive it, then what does it mean to be conscious in a world where past, present, and future are indistinguishable? Some philosophers and neuroscientists suggest that our perception of time is closely tied to the way our brains process information. The brain constructs a continuous stream of consciousness by piecing together discrete moments of sensory input, much like a film projector creates the illusion of motion by rapidly displaying still images. In this view, time may be a mental construct, a way for our brains to make sense of the universe. Just as we perceive colors that do not exist outside our minds, color is merely the brain's interpretation of different wavelengths of light, we might perceive time as a flow when it is, in fact, static. This idea is bolstered by research into altered states of consciousness, such as meditation, psychedelic experiences, and certain neurological conditions, in which individuals report a breakdown of the usual perception of time. In these states, people often describe a sense of timelessness, or the feeling that past, present, and future are all one. Such experiences suggest that our perception of time is flexible and can be altered, reinforcing the idea that time might be a mental construct. Ultimately, the question of whether time is an illusion touches on some of the deepest mysteries of existence. If time does not exist as we perceive it, then our understanding of reality, causality, and even the nature of life and death might need to be re-evaluated. Time, in this view, could be akin to a trick of the mind, a useful but ultimately flawed way of organizing our experiences. Physicists continue to wrestle with the concept of time, seeking something called a theory of everything. Some suggest that such a theory might reveal that time, as we understand it, does not exist at the most fundamental level of reality. If this is true, then the implications for our understanding of the universe and our place in it are staggering. But what exactly is a theory of everything? Well, put simply, a theory of everything would encompass all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Today, we have two primary frameworks that describe these forces: general relativity, which accounts for gravity and large-scale structures like stars and galaxies, and quantum mechanics, which explains the behavior of particles at microscopic scales. However, these two theories are fundamentally incompatible. General relativity sees space and time as continuous, while quantum mechanics treats them as quantized and probabilistic. Bridging this gap is the central challenge for a theory of everything. Albert Einstein's general theory of relativity, formulated in 1915, revolutionized our understanding of gravity. In Einstein's view, gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time, causing other objects to move in response to that curvature. This insight replaced the Newtonian idea of gravity as a force acting at a distance and explained a variety of phenomena that Newtonian mechanics could not, such as the precise orbit of Mercury and the bending of light around massive objects, gravitational lensing. General relativity has been incredibly successful in describing large-scale phenomena, such as the dynamics of galaxies and the expansion of the universe. However, it breaks down at extremely small scales, particularly in describing the center of black holes or the conditions of the universe just after the Big Bang. At these scales, quantum effects become significant, and general relativity alone cannot provide a complete picture. Quantum mechanics, developed in the early 20th century by scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, provides a detailed description of the interactions between subatomic particles. Unlike general relativity, quantum mechanics deals with probabilities rather than certainties. The behavior of particles is governed by wave functions, which describe the probability of finding a particle in a particular state. This probabilistic nature is fundamentally different from the deterministic view of space-time in general relativity. One of the triumphs of quantum mechanics is the standard model of particle physics, which unifies three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. The standard model successfully describes a wide range of particle interactions and has been confirmed through countless experiments. However, it does not include gravity, the fourth fundamental force, nor does it explain certain cosmological mysteries, such as dark matter and dark energy. The biggest obstacle to a theory of everything is gravity. While general relativity beautifully explains gravity at large scales, it doesn't work at quantum scales. When physicists try to apply quantum mechanics to gravitational fields, they encounter infinities, mathematical quantities that make no physical sense. This issue becomes especially critical in extreme environments, such as black holes, where both quantum effects and gravitational effects are significant. The mathematical incompatibility of gravity and quantum mechanics suggests that we are missing a deeper theory that can unify them. Physicists believe that gravity must have a quantum description, but no one has yet found a consistent theory that works in all situations. This has led to the search for new ideas, such as quantum gravity, which could unify general relativity and quantum mechanics under one framework. One of the most prominent attempts to develop a theory of everything is string theory. In string theory, the fundamental building blocks of the universe are not point particles, as in the standard model, but rather tiny, vibrating strings. These strings can vibrate in different ways, and the different patterns of vibration correspond to different particles. In this framework, gravity emerges naturally as one of the vibrational modes of the strings, thereby incorporating gravity into a quantum framework. String theory also introduces the concept of extra dimensions. While we are familiar with 3 dimensions of space and 1 dimension of time, string theory suggests that there may be additional hidden dimensions that are compactified, curled up so small that they are imperceptible to us. These extra dimensions could help explain why gravity is so much weaker than the other fundamental forces, as it may be spread out over these additional dimensions. However, string theory is far from proven. One of its major criticisms is that it is not experimentally testable in any practical sense. The energy scales required to probe the structure of strings are so high that they are beyond the reach of current or foreseeable technology. This has led some physicists to question whether string theory is truly a scientific theory, as it currently lacks the ability to make falsifiable predictions. Another approach to unifying gravity and quantum mechanics is loop quantum gravity. Unlike string theory, which attempts to replace point particles with strings, loop quantum gravity works directly with the fabric of spacetime itself. It proposes that spacetime is quantized at the smallest scales, forming a network of discrete loops. These loops form a kind of atomic structure of space, similar to how matter is made up of atoms. Loop quantum gravity has had some success in explaining certain phenomena, such as the behavior of black holes and the Big Bang. However, like string theory, it is not yet complete, and much work remains to be done before it can be considered a viable theory of everything. Any theory of everything must also account for two of the biggest mysteries in modern cosmology: dark matter and dark energy. Dark matter is one of the most critical ingredients in the universe, but it's something we cannot directly observe. It doesn't emit, absorb, or reflect light, which makes it invisible to telescopes. Instead, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, many of the structures we see in the universe today, from galaxies to massive clusters of galaxies, would not have formed. The first hint of dark matter's existence came in the 1930s when Swiss astronomer Fritz Zwicky observed the Coma cluster, a collection of galaxies. Zwicky noticed that the galaxies in the cluster were moving much faster than expected based on the visible matter alone. To account for this discrepancy, he proposed the existence of missing mass, what we now refer to as dark matter. Further evidence came in the 1970s when astronomer Vera Rubin studied the rotation curves of spiral galaxies. Rubin found that stars at the outer edges of galaxies were moving just as fast as stars closer to the center, a puzzling result because, according to Newtonian mechanics, the stars on the outskirts should be moving slower if only visible matter was present. The explanation for this anomaly was that an unseen mass, dark matter, was providing the necessary gravitational pull to keep those stars moving at such high speeds. While dark matter has been established as a critical player in the universe's evolution, its composition remains a mystery. One prevailing theory suggests that dark matter is made of WIMPs, for weakly interacting massive particles. These hypothetical particles would interact with regular matter only through gravity and the weak nuclear force, making them difficult to detect. Despite several experiments designed to catch a glimpse of WIMPs, including underground detectors and particle accelerators like the Large Hadron Collider, LHC, none have yet provided definitive evidence. Another theory posits that dark matter could be composed of axions, ultralight particles that might also interact weakly with ordinary matter. Like WIMPs, axions have eluded detection, but ongoing experiments continue to search for them. There are also alternative explanations for dark matter's gravitational effects. Modified Newtonian dynamics, also known as MOND, is a theory that suggests the laws of gravity might need to be tweaked to explain galaxy rotation curves without invoking dark matter. However, MOND struggles to explain the full range of cosmological observations, such as the cosmic microwave background and the formation of large-scale structures in the universe, where dark matter plays a central role. Despite its invisibility, dark matter is essential to the universe's structure. It acts like an invisible scaffolding upon which galaxies form and grow. Without dark matter, the early universe's matter density wouldn't have been enough to pull together into galaxies and clusters through gravity alone. Furthermore, dark matter's gravitational effects are critical in the study of cosmic phenomena, like gravitational lensing, where massive objects bend light from distant sources. Observing these light-bending effects allows astronomers to map out where dark matter is located, even though it remains unseen. While dark matter explains the gravitational forces holding galaxies together, dark energy addresses a completely different mystery: the accelerating expansion of the universe. Rate. In the 1990s, two independent teams of astronomers were studying distant supernovae to measure the universe's expansion rate. They expected to find that the expansion was slowing down, as gravity from matter should be pulling everything back together. Instead, they found the opposite. The universe's expansion was accelerating. This was a shocking discovery, as it implied the existence of a new, unseen force that was pushing galaxies apart. To explain this unexpected acceleration, cosmologists introduced the concept of dark energy. However, dark energy is even more elusive than dark matter, and its nature remains largely speculative. One leading hypothesis is that dark energy is related to the cosmological constant, first introduced by Albert Einstein. In his theory of general relativity, Einstein included a term called the cosmological constant, which acted as a repulsive force to counteract gravity and keep the universe static. After Edwin Hubble's discovery of the expanding universe, Einstein abandoned the idea, calling it his greatest blunder. However, the discovery of the accelerating universe brought the cosmological constant back into play as a potential explanation for dark energy. In this context, dark energy could be thought of as a property of space itself. As space expands, the energy density associated with dark energy remains constant, leading to the universe's accelerated expansion. This model fits current observations well, but it leaves many questions unanswered. For example, why does dark energy have the value it does? If the cosmological constant were slightly different, the universe might have expanded too rapidly for galaxies to form, or it might have collapsed in on itself. Another possibility is that dark energy is related to a dynamic field known as quintessence, which evolves over time. Unlike the cosmological constant, quintessence would change its strength as the universe expands, potentially providing a more flexible explanation for dark energy's effects. Dark energy is the dominant component of the universe, making up about 68% of its total energy density. Its influence has become more significant over time as the universe expanded. In the early universe, dark matter and radiation played a more prominent role, but as space grew larger, dark energy began to dominate, driving the accelerating expansion we see today. Dark energy has profound implications for the universe's fate. If the acceleration continues indefinitely, the universe will keep expanding, causing galaxies to drift farther apart. Eventually, distant galaxies may become so far removed that their light can no longer reach us, plunging the universe into a big freeze where stars burn out, and all that remains are isolated black holes and cold remnants of once luminous galaxies. Put simply, together, dark matter and dark energy make up about 95% of the universe's total content, but we know very little about their true nature. Neither dark matter nor dark energy is explained by the Standard Model or by general relativity, which suggests that our current understanding of the universe is incomplete. A true theory of everything must not only unify gravity with quantum mechanics, but also explain the existence and behavior of dark matter and dark energy. Thus, despite the progress made in theoretical physics over the past century, the quest for a theory of everything remains unfinished. Some physicists believe that new experimental discoveries, perhaps from high-energy particle colliders or precision measurements of cosmological phenomena, will provide the missing pieces of the puzzle. Others suggest that the very framework of physics may need to be radically rethought, requiring new concepts that go beyond space, time, and matter as we currently understand them. In the end, whether or not such a theory will ever be found remains an open question, but the pursuit itself has already deepened our understanding of the universe and our place within it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
About quark gluon plasma?
That's bad. That's bad for physics. For the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something...
NASA has been at the forefront of space exploration and scientific discovery for decades. Its relentless pursuit of knowledge has unveiled a series of discoveries that have profoundly altered our understanding of the universe. From distant galaxies and black holes to the early moments after the Big Bang, NASA's missions have expanded the horizons of human knowledge, challenging existing paradigms and fostering new theories. Join us in today's episode as we dig deep into the most significant discoveries that have reshaped our comprehension of the cosmos. Number 1. The cosmic microwave background radiation, the afterglow of creation. One of NASA's most significant contributions to cosmology is the discovery and mapping of the CMB, for cosmic microwave background radiation. The CMB is the faint afterglow of the Big Bang, the primordial explosion that gave birth to the universe approximately 13.8 billion years ago. This discovery provided critical evidence supporting the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB was first detected by accident in 1965 by Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics for their work. However, it was NASA's Cosmic Background Explorer, COBE, satellite, launched in 1989, that provided the first detailed map of the CMB. COBE's data confirmed that the CMB was almost perfectly uniform across the sky, with tiny fluctuations that represented the seeds of all the current structures in the universe, such as galaxies and clusters of galaxies. These tiny fluctuations in the CMB provided crucial insights into the early universe's conditions, helping to refine the Big Bang theory and leading to a better understanding of the universe's age, composition, and development. The COBE mission was followed by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, both of which provided even more detailed measurements of the CMB. These missions allowed scientists to determine that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, a mysterious force driving the universe's accelerated expansion. The discovery and study of the CMB have been foundational in cosmology, providing a baby picture of the universe that has shaped our understanding of everything from the nature of matter and energy to the ultimate fate of the cosmos. Number 2. The accelerating expansion of the universe, unveiling dark energy. In the late 1990s, one of the most groundbreaking discoveries in astronomy was made using data from NASA's Hubble Space Telescope. Scientists found that the expansion of the universe is not slowing down, as previously thought, but is actually accelerating. This discovery was a complete surprise and led to the introduction of the concept of dark energy, a mysterious force that permeates all of space and is driving the universe's accelerated expansion. The discovery was made by observing distant Type Ia supernovae, which are exploding stars that can be used as standard candles to measure distances in the universe. By comparing the brightness of these supernovae at different distances, scientists found that distant galaxies were moving away from us faster than nearby ones, indicating that the universe's expansion rate was increasing over time. The implications of this discovery are profound. Dark energy, which is believed to make up about 68% of the universe, remains one of the biggest mysteries in modern physics. Its discovery has led to a fundamental shift in our understanding of the universe, suggesting that the cosmos could continue expanding forever, potentially leading to a big freeze where galaxies drift apart, stars burn out, and the universe becomes a cold, dark place. NASA continues to study dark energy through various missions, including the upcoming Nancy Grace Roman Space Telescope, which aims to explore the nature of dark energy by measuring the distribution of galaxies across cosmic time. The discovery of dark energy is a testament to the unexpected ways the universe continues to surprise us, challenging our theories and pushing the boundaries of our knowledge. Number 3. The discovery of exoplanets, expanding the search for life. One of the most exciting and transformative discoveries made by NASA in recent decades is the detection of exoplanets, planets orbiting stars outside our solar system. This search was revolutionized by NASA's Kepler Space Telescope, launched in 2009, which was designed to monitor over 150,000 stars in a small patch of the Milky Way galaxy. Kepler's mission was to look for tiny dips in a star's brightness that occur when a planet passes in front of it, a method known as the transit method. Kepler's results were astonishing. The telescope discovered over 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. These discoveries revealed that planets are not rare, but are common throughout the galaxy, with estimates suggesting that there are more planets than stars in the Milky Way. Among these exoplanets, several have been found in the habitable zone of their stars, the region where conditions might be right for liquid water to exist on a planet's surface, which is considered a key ingredient for life. One of the most famous of these is Kepler 186, an Earth-sized planet located in the habitable zone of its star. This discovery has profound implications for the search for extraterrestrial life, suggesting that there may be billions of potentially habitable worlds in our galaxy alone. The discovery of exoplanets has opened up a new field of astronomy, with NASA continuing to lead the search for life beyond our solar system. The Transiting Exoplanet Survey satellite, also known as TESS, launched in 2018, is continuing Kepler's work by surveying the entire sky for exoplanets. Meanwhile, the James Webb Space Telescope, JWST, launched in 2021, is poised to study the atmospheres of these distant worlds in unprecedented detail, searching for signs of life. The discovery of exoplanets has fundamentally changed our understanding of the universe, revealing that our solar system is just one of countless planetary systems scattered throughout the galaxy. It has also reignited the age-old question: are we alone in the universe? NASA's ongoing search for exoplanets and the conditions for life continues to bring us closer to answering this question. Number 4. The observation of gravitational waves, a new window into the universe. In 2015, scientists made the first direct observation of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, such as the collision of black holes. This discovery, which confirmed a major prediction of Albert Einstein's theory of general relativity, was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a project with significant contributions from NASA. Gravitational waves were first predicted by Einstein in 1915 as part of his theory of general relativity, which describes gravity as the warping of space and time by massive objects. However, detecting these waves proved to be an enormous challenge due to their incredibly faint nature. LIGO, which consists of 2 facilities in the United States, was designed to detect these minuscule ripples by measuring the tiny distortions they cause as they pass through Earth. The first detection of gravitational waves came from the merger of 2 black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. This event was named GWW15914 and marked the beginning of a new era in astronomy, gravitational wave astronomy. The ability to detect and study gravitational waves has opened up a completely new way of observing the universe. Unlike light, gravitational waves are not easily absorbed or scattered, allowing them to carry information about the most violent and energetic events in the cosmos, such as black hole mergers, neutron-star collisions, and even events from the early universe. Since the first detection, LIGO, along with its European counterpart Virgo, has detected dozens of gravitational wave events, providing new insights into the nature of black holes, the structure of neutron stars, and the behavior of matter under extreme conditions. These observations have confirmed that black holes are common throughout the universe and have provided a new way to test the limits of Einstein's theory. Looking ahead, NASA is collaborating on LISA for the Laser Interferometer Space Antenna, a space-based gravitational wave detector that will be sensitive to a different range of gravitational waves than LIGO, potentially revealing new physics and shedding light on the most mysterious phenomena in the universe. Number 5. The exploration of Mars. Searching for life on the red planet. NASA's exploration of Mars has been one of its most enduring and scientifically rewarding endeavors. Since the 1960s, NASA has sent a series of missions to Mars, each more sophisticated than the last, culminating in the recent Mars rovers, such as Curiosity and Perseverance, which have transformed our understanding of the red planet and its potential to host life. One of the most groundbreaking discoveries on Mars came from the Curiosity rover, which landed in Gale Crater in 2012. Curiosity found evidence that Mars once had conditions suitable for life, including ancient riverbeds, lakes, and the presence of key chemical ingredients for life, such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Curiosity also detected complex organic molecules in Martian soil, which, while not proof of life, are the building blocks of life as we know it. The Perseverance rover, which landed in Jezero Crater in 2021, is continuing this search for life. Jezero Crater was chosen as the landing site because it is believed to have once been a lake, with river deltas that could have preserved signs of ancient microbial life. Perseverance is equipped with advanced scientific instruments to analyze rocks and soil, searching for biosignatures, chemical or physical signs of past life. One of Perseverance's most ambitious goals is to collect samples of Martian rock and soil that will be returned to Earth by a future mission. This will allow scientists to study Martian material in unprecedented detail, potentially providing the first direct evidence of life beyond Earth. NASA's Mars exploration program has not only provided evidence that Mars was once habitable, but it has also laid the groundwork for future human exploration. For example, the discovery of water ice on Mars suggests that future astronauts could extract water for drinking and producing oxygen and rocket fuel, making long-term human missions to Mars feasible. As NASA prepares for the next steps in Mars exploration, including the potential human exploration of Mars in the 2030s, the discoveries made by missions like Curiosity and Perseverance will continue to be a vital foundation for our understanding of the red planet and its potential to support life. Number 6. The structure of the Milky Way. For centuries, the true shape and extent of the Milky Way remained elusive due to our position within it. However, through the use of advanced telescopes and space missions, NASA has unveiled the intricate details of the galaxy's architecture. The Milky Way is a barred spiral galaxy, characterized by a central bar-shaped region of stars and a disk composed of several spiral arms. These spiral arms, filled with gas, dust, and young stars, wind out from the central bulge, which houses older stars and a supermassive black hole known as Sagittarius A. The galaxy's disk is relatively thin, but it extends for about 100,000 light-years across, with the Sun located about 26,000 light-years from the galactic center, nestled in the Orion Arm. One of the most significant breakthroughs in mapping the Milky Way came from the NASA-led Cosmic Background Explorer, or COBE, and later, the Spitzer Space Telescope. COBE helped confirm the Milky Way's spiral structure by detecting the distribution of stars and dust in infrared light, which penetrates the dense interstellar dust that obscures visible light. Spitzer further refined this view, revealing the intricate details of the galaxy's arms and confirming the presence of the central bar. In addition, NASA's WMAP and the European Space Agency's Gaia mission have provided crucial data about the Milky Way's shape and size. Gaia, in particular, has mapped the positions and motions of over 1 billion stars, giving astronomers an unprecedented 3D view of the galaxy. This data has helped confirm that the Milky Way is not a simple disk, but has a warped shape, likely caused by interactions with neighboring galaxies, such as the Sagittarius dwarf galaxy. Moreover, NASA's Fermi Gamma Ray Space Telescope has uncovered evidence of massive bubbles of high-energy radiation extending above and below the Milky Way's disk. These Fermi bubbles are thought to be remnants of an energetic event in the galaxy's past, possibly linked to activity from Sagittarius A. NASA's efforts to map and understand the structure of the Milky Way have not only expanded our knowledge of our galaxy, but have also provided insights into the processes that shape galaxies across the universe. This research continues to evolve, offering new glimpses into the dynamic and ever-changing nature of the Milky Way. Number 7. The exploration of the outer solar system. NASA's Voyager exploration of the outer solar system represents one of the most ambitious and successful endeavors in the history of space exploration. Launched in 1977, Voyager 1 and Voyager 2 were initially designed to take advantage of a rare planetary alignment that allowed them to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, using gravity assists to propel them from one destination to the next. This grand tour of the solar system provided humanity with its first close-up views of these distant worlds, fundamentally changing our understanding of the outer planets and their moons. Voyager 1 was the first of the two spacecraft to launch and quickly became the first human-made object to fly by Jupiter in 1979. The data it sent back revealed the planet's turbulent atmosphere, with its great red spot, a massive storm larger than Earth, and its complex system of moons. Particularly significant was the discovery of active volcanoes on Io, one of Jupiter's moons, making it the first body beyond Earth known to be volcanically active. Voyager 1 then proceeded to Saturn in 1980, where it captured detailed images of the planet's rings and discovered new moons. It also provided a closer look at Titan, Saturn's largest moon, revealing its thick atmosphere, which scientists believe might harbor conditions similar to early Earth. Voyager 2 followed a similar path, but went on to achieve what no other spacecraft has done. It visited Uranus in 1986 and Neptune in 1989. The flyby of Uranus uncovered a magnetic field tilted at a bizarre angle and 11 new moons. Voyager 2's encounter with Neptune provided the first images of the planet's dynamic atmosphere, including the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, and the discovery of geysers on Triton, Neptune's largest moon. After completing their primary missions, both Voyager spacecraft continued on their paths out of the solar system, with Voyager 1 becoming the first spacecraft to enter interstellar space in 2012, followed by Voyager 2 in 2018. As of 2024, Voyager 1 is about 15 billion miles from Earth, and Voyager 2 is around 13 billion miles. These distances are vast, but the twins still send data back to Earth by using their onboard instruments and radio communication systems. The signals they send take over 20 hours to reach Earth, traveling at the speed of light. Despite their distance, the spacecraft continue to transmit valuable scientific information about the space environment they encounter as they journey through the outer reaches of the solar system and into interstellar space. The data they send back is helping scientists learn more about the heliosphere, the protective bubble created by the sun's solar wind, and the interstellar medium beyond it. This information is crucial for understanding how our solar system interacts with the surrounding galaxy and provides a glimpse into the conditions of interstellar space, a region that has remained largely unexplored until now. Number 8. The Hubble Deep Field and the Evolution of Galaxies. The Hubble Deep Field represents one of the most profound observational campaigns in the history of astronomy. Conducted by the Hubble Space Telescope in 1995, this initiative aimed to peer into the farthest reaches of the universe, revealing a patch of sky in the constellation Ursa Major that was seemingly empty and devoid of stars or galaxies. Over 10 consecutive days, Hubble captured light from this tiny region, about 1/24 millionth of the sky. creating an image that forever changed our understanding of the universe. The Hubble Deep Field revealed a staggering number of galaxies, nearly 3,000, in a minuscule portion of the sky. These galaxies varied greatly in shape, size, and color, indicating a broad spectrum of ages and evolutionary stages. Some of the galaxies were relatively close to Earth, while others were billions of light-years away, meaning Hubble was capturing images of these galaxies as they appeared when the universe was just a fraction of its current age. This unprecedented glimpse into the early universe offered astronomers crucial insights into the evolution of galaxies. The Hubble Deep Field provided a timeline that spanned billions of years, showing how galaxies have changed over cosmic time. Some of the most distant galaxies in the Hubble Deep Field were small and irregular, suggesting that they were in the early stages of formation. This observation supports the theory that galaxies began as small structures that merged and grew into the massive galaxies we see today, like the Milky Way. Moreover, the diversity of galaxies observed in the Hubble Deep Field, from spirals to ellipticals to peculiar shapes, helped scientists piece together the processes that drive galaxy evolution. For instance, the presence of blue, star-forming galaxies alongside older, redder galaxies indicated that star formation was more rampant in the early universe and has since slowed down. The Hubble Deep Field also highlighted the importance of dark matter in galaxy formation. The distribution and interaction of galaxies in the field suggested that dark matter played a crucial role in their evolution, influencing their shapes and the rate at which they merged with others. Overall, the Hubble Deep Field provided a window into the universe's distant past, offering a profound understanding of how galaxies evolve over time. It set the stage for future deep-field observations and remains a cornerstone in our quest to understand the origins and fate of galaxies in the cosmos. Number 9. The exploration of the Kuiper Belt and the discovery of Pluto's geology. The Kuiper Belt, a distant and icy region of the solar system, represents one of the last frontiers of planetary exploration. Located beyond Neptune's orbit, this vast donut-shaped disk is home to countless icy bodies, dwarf planets, and remnants from the early solar system. First proposed by astronomer Gerard Kuiper in 1951, the Kuiper Belt was hypothesized as a region containing small, icy bodies left over from the solar system's formation. It wasn't until the early 1990s that the first Kuiper Belt object was discovered, confirming the existence of this distant region. The Kuiper Belt extends from about 30 to 55 astronomical units from the Sun, with its objects composed primarily of frozen volatiles such as water, ammonia, and methane. The discovery of the Kuiper Belt provided critical insights into the origins of short-period comets and the early solar system's formation processes. As a reservoir of ancient material, the Kuiper Belt holds the potential to reveal secrets about the solar system's birth and the processes that led to the formation of planets. The most significant milestone in the exploration of the Kuiper Belt came with NASA's New Horizons mission. Launched in 2006, New Horizons was the first spacecraft designed to explore this distant region, with its primary target being Pluto, the most famous of the Kuiper Belt's inhabitants. After a journey of nearly a decade, New Horizons made its historic flyby of Pluto in July 2015, providing humanity with its first close-up images and data from this enigmatic dwarf planet. The flyby revealed Pluto as a complex and geologically active world, shattering previous assumptions that it was a frozen, inert body. New Horizons sent back images of towering mountains of water ice, vast plains of nitrogen ice, and signs of cryovolcanism. The mission's success highlighted the importance of exploring the Kuiper Belt, showing that even at the solar system's fringes, planetary bodies could be dynamic and diverse. Following its successful flyby of Pluto, New Horizons continued its journey deeper into the Kuiper Belt. On January 1, 2019, it made a close approach to another Kuiper Belt object, Arrokoth, previously known as 2014 MU69. This small, bilobed object provided scientists with a glimpse into the early solar system's building blocks. Arrokoth's shape and surface features suggested that it formed through the gentle merging of two smaller bodies, providing valuable insights into how planets and other solar system bodies might have formed. The exploration of Arrokoth and other Kuiper Belt objects has deepened our understanding of the Kuiper Belt as a repository of primordial material. These objects have remained largely unchanged since the solar system's formation, preserving the conditions of the early solar nebula. By studying them, scientists can gain a clearer picture of the processes that led to the formation of planets and the evolution of the solar system. On the other hand, note that the exploration of the Kuiper Belt is still in its early stages, with much left to discover. Future missions could target other Kuiper Belt objects, including larger and more distant objects, to further unravel the mysteries of this remote region. The Kuiper Belt also presents a valuable opportunity to study the formation of planetary systems in other star systems, as it shares similarities with the debris disks observed around young stars. Moreover, the continued exploration of the Kuiper Belt has implications for our understanding of the solar system's boundaries. The region marks the transition from the solar system's planetary zone to the more distant and diffuse Oort cloud, the source of long-period comets. Understanding the Kuiper Belt's structure and population is key to comprehending the solar system's architecture and its interaction with the interstellar environment. Number 10. The first images of black holes and the Event Horizon Telescope. Black holes has long fascinated scientists and the public alike, largely because of the enigmatic nature of their cosmic giants. They are regions of space-time where gravity is so intense that nothing, not even light, can escape. This makes them invisible against the backdrop of space, but their presence can be inferred from their effects on nearby matter and radiation. A groundbreaking tool in the study of black holes has been the Event Horizon Telescope, also known as EHT, an international collaboration that aims to capture images of these elusive objects. It could be said that the EHT represents a monumental leap forward in observational astronomy. The project began in earnest in 2012, bringing together over 200 researchers from institutions worldwide with the goal of imaging the event horizon of a black hole. The EHT is not a single telescope, but a network of radio telescopes located at different points around the globe. By synchronizing these telescopes through a technique called very long baseline interferometry, the EHT effectively creates a planet-sized observatory with unprecedented resolution. The EHT's first major achievement was the release of the image of the supermassive black hole in the galaxy M87 in April 2019. This was a historic moment in astrophysics, as it provided the first direct visual evidence of a black hole's existence. The image showed a bright ring-like structure with a dark central region representing the shadow of the black hole against the glowing gas and plasma surrounding it. This groundbreaking result confirmed many predictions of general relativity and provided new insights into the structure and behavior of black holes. The success of the EHT then has paved the way for further explorations into the nature of black holes. Future improvements in the array, including the addition of more telescopes and the use of higher frequency observations, are expected to enhance the resolution and detail of the images. Upcoming observations will focus not only on refining the image of M87's black hole, but also on imaging the event horizon of the black hole at the center of our own Milky Way galaxy, known as Sagittarius A. Additionally, the EHT's findings are likely to have broader implications for our understanding of fundamental physics. For example, studying the behavior of matter and radiation near the event horizon may provide insights into the nature of space-time, the formation of black holes, and the processes governing their growth and interactions with their surroundings. In summary, the study of black holes and the contributions of the Event Horizon Telescope represent a profound leap in our understanding of the universe. By capturing images of these cosmic behemoths, the EHT has provided a direct glimpse into regions that were previously beyond the reach of observational astronomy, opening up new avenues for research and deepening our understanding of the most extreme objects in the cosmos. Number 11. The James Webb Space Telescope and the Early Universe. The James Webb Space Telescope has opened a new era of cosmology. Launched on December 25, 2021, Webb's advanced capabilities have significantly transformed our comprehension of the early universe, providing unprecedented insights into the cosmos's infancy. At its core, Webb's ability to peer deep into the universe is facilitated by its large, segmented mirror and its position in orbit around the second Lagrange point, about 1.5 million kilometers from Earth. This strategic location, combined with its infrared-optimized instrumentation, allows the telescope to observe the faintest and most distant objects in the universe, those that were previously beyond the reach of earlier telescopes like Hubble. One of the most groundbreaking contributions of James Webb is its capability to observe the universe's first galaxies. By looking back in time through the infrared spectrum, the telescope can detect the light from the earliest galaxies that formed shortly after the Big Bang, about 13.8 billion years ago. These observations have provided new insights into the formation and evolution of the first galaxies, revealing that galaxy formation occurred much earlier than previously thought. For instance, James Webb has identified galaxies formed only a few hundred million years after the Big Bang, challenging previous models of galaxy evolution and pushing the boundaries of our knowledge about how these structures emerged. Webb's deep-field observations have also shed light on the process of reionization, a pivotal era in the universe's history when the first stars and galaxies ionized the intergalactic medium. This period marked the transition from the cosmic dark ages to a universe filled with light. By examining the distribution and characteristics of early galaxies, James Webb has provided crucial data on the timing and nature of reionization, offering a more detailed picture of how the first cosmic structures interacted with their surroundings and contributed to the reionization of the universe. Moreover, the observatory has made significant strides in understanding the formation of stars and planetary systems. Its high-resolution infrared imaging allows scientists to observe star-forming regions obscured by cosmic dust, revealing previously hidden details about the birth of stars and the formation of protoplanetary disks. These observations are crucial for understanding the processes that lead to the formation of planetary systems, including our own. By studying these early star-forming regions, James Webb helps bridge the gap between the initial formation of stars and the eventual development of planetary systems, offering insights into the conditions that might lead to habitable planets. Another critical aspect of James Webb's mission is its ability to study the physical and chemical properties of the early universe. Through its advanced spectroscopic capabilities, the Webb telescope can analyze the light from distant galaxies and stellar objects to determine their composition, temperature, and other fundamental properties. This information is vital for understanding the chemical evolution of the universe, including the formation of heavy elements and the enrichment of the interstellar medium. By examining the spectral signatures of early galaxies and stars, James Webb provides a detailed account of how these objects contributed to the chemical makeup of the universe. In addition to its observational capabilities, findings made by James Webb have prompted a re-evaluation of theoretical models of cosmic evolution. Its data has led to new hypotheses about the formation and growth of galaxies, the nature of dark matter, and the conditions that led to the development of complex structures in the universe. These insights are reshaping our understanding of cosmological processes and prompting revisions to existing models of the early universe. The impact of James Webb extends beyond the immediate realm of galaxy and star formation. Its observations have provided a broader context for understanding the fundamental processes that shaped the universe's structure. By offering a clearer picture of the early universe, the Supreme Observatory helps scientists address some of the most profound questions in cosmology, including the nature of dark energy, the formation of the first black holes, and the origins of cosmic inflation. In summary, thanks to its advanced observational capabilities and infrared technology, the Premier telescope has dramatically enhanced our knowledge of the cosmos's infancy. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. James Webb is living up its billing as a game changer in our quest to understand the universe. Built to succeed the Hubble Space Telescope, James Webb promised to peer farther into the cosmos than any instrument before it, capturing light from the very first stars and galaxies that emerged after the Big Bang. But even in the most optimistic scenarios, scientists were unprepared for what Webb would find. By all existing theories, shouldn't exist. That raised the question, is it time to say goodbye to the Big Bang Theory? Join us as we dig deep into how James Webb could shatter out cosmology in pieces. Theoretically, our picture of the universe isn't particularly malleable, at least on cosmic scales. We already have a suite of observations that cannot be ignored. Everything else that we learn has to be explained within the same context as what we already know. In the early stages of the hot Big Bang, we know that there was an initial spectrum of density imperfections, underdense and overdense regions that appear on all cosmic scales at approximately the 1 part in 30,000 level. We observe these imperfections in the cosmic microwave background, the leftover radiation from the aftermath of the Big Bang, which were imprinted just 380,000 years after the hot Big Bang's beginning. We also know that initially there were no stars or galaxies, and that the universe took substantial amounts of time, at least tens of millions of years, for the very first stars to form. Early on in cosmic history, galaxies were smaller, less massive, less structurally evolved, with fewer heavy elements, and dominated by bluer, younger populations of stars compared to galaxies today. We knew what the universe was like in its very early stages, and we knew what the universe was like once galaxies became abundant, right up to the limits of observatories like the Hubble Space Telescope. But what would James Webb discover? In order to find out, we had to acquire those critical observations. Some of what the telescope found was expected, at least by some. The cosmic distance record for the most distant object was broken several times, as was the record for the most distant galaxy cluster, the most distant gravitational lens, along with numerous other revolutionary finds. Some of the things that James Webb saw were on the fringes of what we expected to be there. Large numbers of early galaxies that strained the limits of how massive we thought galaxies could get to be after such short periods of time. And some of what James Webb saw was wholly unexpected by almost everyone, such as the presence of early, supermassive black holes that clearly didn't form from the stars present within the early proto-galaxies that hosted them. Among the more unexpected finds were the presence and abundance of these little red dots, which we swiftly realized were primarily due to early, bright galaxies that appeared very shortly after the Big Bang in terms of cosmic history. Although a few of these galaxies turned out to be intrinsically red objects that were less distant, and hence, from later times in the universe's history, most of the little red dots truly did correspond to young, bright galaxies. Moreover, the number of little red dot galaxies that we were finding was truly stretching the limits of what simulations indicated was possible. Why were there so many of these very bright galaxies at such early times? This was one of the key puzzles that astronomers and astrophysicists had to face when confronted with the novel Webb data. It's easy to declare, "No one expected this," and even easier to leap to a fantastical conclusion, such as, "Cosmology is broken," or "Our model of the universe can't be reconciled with these observations." But much more challenging, at least from a scientific perspective, is to look at the unexpected and try to find the underlying explanation for how these objects came to be. After all, it was the Hubble Space Telescope that revealed to humanity what the universe looked like. But it would fall to James Webb to teach us how the universe grew up and came to be the way that it is today. In other words, James Webb has broken our understanding of the universe in pieces. As a result, we now are rewriting all the textbooks of cosmic history. The first thing people took a detailed look at was the performance of James Webb itself. One of the most important aspects of any telescope isn't just understanding properties, like its resolution, light-gathering power, and wavelength sensitivity, but a mandatory understanding of how the entire optical system works, as well as the efficiency of that system. No telescope is optically perfect, as there are always losses due to reflections off of surfaces, any dust or dirt that's accumulated on the optical surfaces, degradations or imperfections in the mirrors themselves, even the tiniest, most minuscule misalignments in the mirrors or instruments, as well as thermal noise and imperfect properties within the instruments themselves. It turned out that when it came to James Webb, scientists had calculated the expected performance of the overall observatory based on these factors. However, when it came to crunch time, the telescope itself turned out to actually outperform those expectations, as James Webb was kept cleaner and more pristine than any other space telescope ever built and constructed. Webb's views of the universe were all at once sharper, lower in noise, and optically more efficient than even the most optimistic of predictions. Its point spread function, also known as PSF, or how well it can focus the light from distant targets, is practically twice as sharp as the design requirements, making it the best telescope ever on this front in human history. This meant that sharper images and fainter point-like objects could be revealed in less time than was anticipated, and also that objects that were revealed would appear brighter than expected in a given amount of observing time. This is important information for properly calibrating any observations acquired with James Webb, as how bright an object appears through your telescope is essential information for determining its intrinsic properties, including how intrinsically bright it is. While this plays a role in the observed brightness of objects seen with James Webb, it couldn't fully explain why these little red dots were so bright and abundant. As a result, many scientists is reconsidering the timeline of galaxy formation. If galaxies captured by James Webb truly existed only a few 100 million years after the Big Bang, it suggests that the universe was able to form large structures much faster than previously thought. One possibility is that the first stars, known as population 3 stars, were far more massive and efficient at forming galaxies than current models suggest. Population 3 stars are thought to have been made entirely of hydrogen and helium, as heavier elements had not yet been forged in the universe. These stars would have burned hotter and faster than stars today, potentially leading to the rapid formation of galaxies. Another theory is that the dark matter, which makes up about 85% of the universe's mass, played a more significant role in the early universe than previously thought. Dark matter could have clumped together more quickly, providing the gravitational wells necessary for galaxies to form and grow at an accelerated pace. Some scientists have even suggested that Webb's findings could point to new physics beyond the standard model. For instance, modifications to the laws of gravity on cosmic scales or the existence of unknown particles could help explain the rapid formation of these galaxies. While these ideas remain speculative, discoveries made by James Webb have undoubtedly opened the door to new and exciting possibilities in our understanding of the cosmos. Notably, the discovery of impossible galaxies not only challenges our understanding of galaxy formation, but also has profound implications for the entire history of the universe. If galaxies could form and evolve so quickly, it suggests that the universe may have been a more dynamic and violent place in its early years than we previously imagined. The existence of massive galaxies so soon after the Big Bang also raises questions about the reionization era, a period about 400 million to 1 billion years after the Big Bang, when the first stars and galaxies ionized the neutral hydrogen that filled the universe. If Webb's galaxies were already in existence, they may have played a significant role in reionizing the universe, helping to clear the fog of neutral hydrogen and making the universe transparent to light. Moreover, these findings could have a ripple effect on our understanding of the large-scale structure of the universe. The standard model of cosmology is built on the idea that the universe is homogeneous and isotropic, meaning it looks the same in every direction on large scales. However, the presence of massive galaxies in the early universe suggests that there may have been significant variations in density and structure, leading to a more clumpy and uneven cosmos than previously thought. Another area where James Webb is shaking up our understanding is the presence of supermassive black holes in the early universe. Supermassive black holes, which contain millions or even billions of times the mass of our Sun, are typically found at the centers of galaxies. They play a crucial role in galaxy formation and evolution, influencing the movement of stars, the growth of galaxies, and the behavior of interstellar gas. Until recently, our understanding of these cosmic giants was primarily based on observations from the Hubble Space Telescope and other ground-based observatories, which suggested that supermassive black holes formed gradually over time as galaxies themselves matured. However, the Webb telescope has upended this narrative. By peering back in time to the first few hundred million years after the Big Bang, the telescope has detected supermassive black holes that existed when the universe was still in its infancy. These black holes are not just anomalies, they appear to be common, indicating that the processes that lead to their formation were already well underway very early in the universe's history. This finding challenges the prevailing theories that suggest black holes and galaxies grow in tandem, gradually accumulating mass as the universe evolves. The discovery of these ancient supermassive black holes forces astrophysicists to reconsider the existing models of black hole formation. Traditional theories propose that black holes form from the collapse of massive stars, gradually growing by accreting gas, dust, and even other black holes over billions of years. However, James Webb's findings suggest that some black holes must have formed much more rapidly than previously thought. One possibility is that these supermassive black holes originated from so-called direct collapse black holes. In this scenario, instead of forming from the remnants of a star, a massive cloud of gas could collapse directly into a black hole without first forming a star. This process could create a black hole with a mass thousands of times that of the Sun almost instantaneously, providing a potential explanation for the existence of such massive black holes in the early universe. Another theory suggests that these early black holes could have formed from the mergers of smaller black holes or dense clusters of stars. In the dense environments of the early universe, where stars and black holes were packed much more closely together than they are today, such mergers could have occurred frequently, leading to the rapid growth of supermassive black holes. What's notable, similar to Webb's impossible early galaxies, the existence of supermassive black holes in the early universe also poses a significant challenge to our cosmological models, particularly those related to galaxy formation and evolution. According to the standard model of cosmology, galaxies form through the gradual accumulation of matter, with small galaxies merging to form larger ones over time. Supermassive black holes are thought to form at the centers of these galaxies and grow as the galaxies themselves grow. However, observations made by James Webb suggest that supermassive black holes may have formed before the galaxies that host them were fully developed. This raises the possibility that black holes could have played a more central role in galaxy formation than previously thought. Instead of forming in tandem with galaxies, supermassive black holes may have driven the formation of galaxies, with their immense gravitational pull helping to gather the gas and dust needed to create stars and galaxies. This idea turns the conventional wisdom on its head. If black holes are the seeds from which galaxies grow, rather than mere byproducts of galaxy formation, it would require a major revision of our understanding of the universe's history. The precise mechanisms by which supermassive black holes could have influenced galaxy formation are still unclear, and this is likely to be a major focus of astrophysical research in the coming years. In addition, the Webb's discoveries also have implications for our understanding of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter is thought to make up about 27% of the universe's mass-energy content, and it plays a crucial role in the formation of galaxies by providing the gravitational scaffolding that allows ordinary matter to coalesce into stars and galaxies. Dark energy, which makes up about 68% of the universe, is responsible for the accelerated expansion of the universe. The presence of supermassive black holes in the early universe suggests that dark matter may have clumped together more quickly than previously thought, providing the necessary conditions for the rapid formation of black holes. Alternatively, it could indicate that our understanding of dark matter is incomplete, and that other processes are at play in the early universe. Furthermore, the existence of these early black holes could have implications for dark energy. If supermassive black holes formed earlier than expected, it could affect the rate of the universe's expansion, potentially offering new insights into the nature of dark energy and its role in the universe's evolution. While James Webb's primary mission is to study the early universe, it is also equipped to explore exoplanets, planets orbiting stars outside our solar system, and search for signs of life. Before the James Webb era, our knowledge of exoplanets was largely based on indirect observations. Instruments like the Kepler Space Telescope and ground-based observatories discovered thousands of exoplanets, revealing that they are common throughout the galaxy. However, detailed information about these planets was limited. We knew little about their atmospheres, surface conditions, or potential for hosting life. James Webb has ushered in a new era by providing direct observations of exoplanetary atmospheres with unparalleled precision. Its ability to capture infrared light allows it to peer through the thick atmospheres of distant planets, revealing their chemical compositions, temperature profiles, and even weather patterns. This capability has opened up new avenues for understanding the diversity of exoplanets and assessing their potential habitability. One of Webb's most significant contributions to exoplanet science is its ability to analyze the atmospheres of these distant worlds. The telescope's NIR spec and MIRI are capable of detecting the faint signatures of molecules in exoplanet atmospheres. This has allowed scientists to identify key gases such as water vapor, carbon dioxide, methane, and oxygen, molecules that are crucial indicators of a planet's potential to support life. For instance, Webb's observations of the exoplanet WASP-96b, a hot gas giant, revealed the presence of water vapor in its atmosphere. This discovery was a significant milestone, as it demonstrated the telescope's ability to detect water on exoplanets. While WASP-96b is far from habitable due to its scorching temperatures, the detection of water vapor paves the way for similar studies on smaller, potentially habitable planets. In another groundbreaking observation, James Webb detected carbon dioxide in the atmosphere of a super-Earth exoplanet, GJ 1132b, This detection is particularly exciting because carbon dioxide is a key greenhouse gas that can affect a planet's climate and temperature. By analyzing the ratios of different gases, scientists can infer the processes shaping these atmospheres and better understand the conditions on the planet's surface. Besides, James Webb is also shedding light on the processes that govern planetary formation and evolution. By observing young star systems where planets are still forming, the observatory provides valuable insights into how planets accrete material and develop their atmospheres. This is crucial for understanding why exoplanets exhibit such a wide range of sizes, compositions, and orbital configurations. For example, Webb's observations of the protoplanetary disk around the star PDS 70 have revealed intricate details about the formation of gas giants. The telescope detected gaps in the disk, which are likely caused by the gravitational influence of forming planets. These observations help confirm theories about how planets carve out their orbits and interact with the material around them, ultimately shaping the architecture of planetary systems. Furthermore, James Webb is also investigating the mysterious class of planets known as super-Earths. These planets, which are larger than Earth but smaller than Neptune, have puzzled scientists because they have no direct counterparts in our solar system. Its ability to study their atmospheres and compositions is providing clues about their origins and whether they could be rocky worlds with the potential for habitability. One of the most exciting aspects of Webb's mission is its potential to identify habitable exoplanets. By studying planets in the habitable zone of their stars, the region where conditions might allow liquid water to exist, James Webb aims to find worlds that could potentially support life. Webb's infrared capabilities are particularly well suited for studying cooler stars, known as M-dwarfs, which are abundant in our galaxy. These stars are smaller and dimmer than our Sun, so their habitable zones are much closer in. Planets orbiting in these zones are easier to observe with James Webb, making them prime targets in the search for life. One of the key targets for James Webb is the TRAPPIST-1 system, a star system with 7 Earth-sized planets, 3 of which are in the habitable zone. Webb's observations of these planets are expected to provide the most detailed look yet at the atmospheres of potentially habitable worlds. By analyzing the composition of these atmospheres, the telescope could detect signs of biological activity, such as an imbalance of gases that might indicate the presence of life. Moreover, Webb's observations are already challenging some of our preconceived notions about exoplanets. For example, the telescope has revealed that some gas giants, known as hot Jupiters, have highly dynamic atmospheres with extreme weather patterns. These planets, which orbit very close to their stars, experience intense radiation that drives powerful winds and temperature fluctuations. Webb's detailed studies of these atmospheres are helping scientists understand the complex interplay between a planet's atmosphere and its star's radiation. James Webb's observations indicate that these planets might have thick, cloudy atmospheres with complex weather systems, challenging the assumption that they are simple, featureless worlds. As James Webb continues its mission, it will undoubtedly uncover more surprises and deepen our understanding of exoplanets. One of the most exciting prospects for the future is the potential discovery of biomarkers, chemical signatures in exoplanet atmospheres that could indicate the presence of life. Webb's sensitivity to key molecules like oxygen and methane makes it well suited for this task. While detecting life beyond Earth remains a challenging goal, the Supreme Telescope brings us closer than ever to answering one of humanity's most profound questions. Are we alone in the universe? Another remarkable aspect, some findings from the James Webb Space Telescope are prompting scientists to revisit and reconsider cosmic inflation, a cornerstone of modern cosmology, providing a compelling explanation for the uniformity and structure of the universe. Cosmic inflation was proposed in the early 1980s by physicists Alan Guth, Andre Linde, and others as a solution to several puzzling aspects of the Big Bang theory. The primary issue was the horizon problem. How could regions of the universe that are so far apart and seemingly disconnected appear so remarkably similar? Inflation offered an elegant solution by suggesting that the universe underwent a brief but extremely rapid expansion, which would have stretched any initial irregularities across the cosmos and led to the homogeneity we observe today. Another problem inflation addressed was the flatness problem. The universe appears to be remarkably flat, meaning that its geometry is not curved like a sphere or a saddle. This flatness requires extremely fine-tuned initial conditions, something inflation naturally accounts for by driving the universe towards a flat state during its exponential growth. These insights have shaped our understanding of the universe's earliest moments, and inflationary theory has become deeply embedded in the standard cosmological model. However, as with any scientific theory, it remains subject to testing and revision based on new evidence. The Webb telescope, with its unparalleled observational capabilities, is now providing data that may challenge or refine our understanding of cosmic inflation. One of the key predictions of inflationary theory is that the universe should exhibit a specific pattern of temperature fluctuations in the CMB for the cosmic microwave background radiation, which is the afterglow of the Big Bang. These fluctuations arise from quantum fluctuations during inflation, which were then stretched to cosmic scales. The Planck satellite, launched by the European Space Agency in 2009, provided detailed measurements of the CMB and supported the inflationary model by revealing these fluctuations with high precision. However, James Webb offers a different kind of test. By observing the distribution and properties of early galaxies, the telescope can provide insights into the initial conditions of the universe and the processes that shaped its evolution. If the early universe's structure or the rate at which galaxies formed does not align with inflationary predictions, it could suggest that our understanding of this period is incomplete or that alternative theories need to be considered. And unfortunately, since its launch, the Webb telescope has already made several surprising discoveries that have raised questions about the inflationary model. As mentioned, the telescope has observed galaxies that are far more massive and mature than expected for their age. According to the standard model, including inflation, such large and well-formed galaxies should not exist so soon after the Big Bang. These observations suggest that the early universe may have been more complex than previously thought, with processes that challenge our current understanding of how structure formed in the cosmos. Additionally, Webb has detected unexpected patterns in the distribution of these early galaxies. Inflation predicts a nearly uniform distribution of matter on large scales, but some of James Webb's findings hint at the possibility of more pronounced structures or variations than anticipated. These discrepancies could indicate that inflation did not proceed as smoothly as the standard model suggests, or that other processes were at play in shaping the universe's large-scale structure. One potential alternative to the standard inflationary model is the idea of bouncing cosmologies. Simply put, the bouncing cosmologies is reimagining of the universe's cyclical nature. The idea of a cyclic universe itself is not new. Ancient civilizations, such as those in India and Greece, entertained the notion of an eternally repeating cosmos. However, in modern physics, the concept gained traction as scientists sought solutions to some of the unresolved issues in the Big Bang model, particularly the nature of the singularity, the point at which the laws of physics break down. In the 1920s and 1930s, physicists like Richard Tolman began exploring the possibility of a cyclical universe as a way to avoid the singularity problem. Tolman proposed that the universe could expand and then contract in a series of cycles, each beginning with a Big Bang and ending with a Big Crunch. This would allow for a universe with no true beginning or end, where each cycle resets the conditions for the next. In this model, the universe reaches a maximum size before gravitational forces cause it to collapse back into a highly dense state, followed by a new expansion phase. This cyclical process hinges on the behavior of matter, energy, and space-time during these phases. During the expansion phase, the universe cools and spreads out, allowing galaxies, stars, and planets to form. As the universe reaches its maximum extent, the expansion slows and eventually reverses. The contraction phase then begins, where the universe's density increases, temperatures rise, and space-time curvature grows, leading to the formation of a big crunch. Several theories propose different mechanisms for the bounce that transitions the universe from contraction to expansion. One of the leading ideas is rooted in quantum gravity, which suggests that quantum effects prevent the universe from collapsing into a singularity during the Big Crunch. Instead, these effects could create a rebound, causing the universe to bounce and start a new expansion phase. One of the most well-known theories that support a bouncing cosmology is loop quantum gravity, or called LQG. LQG is an attempt to reconcile general relativity, which describes gravity at macroscopic scales, with quantum mechanics, which governs the behavior of particles at the smallest scales. In LQG, space-time is not continuous, but is instead composed of tiny, discrete loops. These loops create a network, or spin network, that forms the fabric of space-time. When the universe contracts and reaches an extremely dense state, LQG predicts that the discrete nature of space-time prevents the formation of a singularity. Instead, the universe's density increases until quantum effects cause a repulsive force, leading to a bounce and subsequent expansion. This idea is compelling because it provides a way to avoid the singularity problem that plagues the Big Bang model. If the universe never reaches an infinite density and temperature, the laws of physics can remain valid throughout the entire cosmological cycle. Another significant approach to bouncing cosmologies is found in the ekpyrotic and cyclic models. These theories are rooted in string theory, a framework that attempts to describe all fundamental forces and particles as one-dimensional strings rather than point-like particles. The ekpyrotic model, proposed in 2001 by Paul Steinhardt, Neil Turok, and others, suggests that the universe's expansion and contraction phases are driven by the interaction of higher-dimensional branes, short for membranes. In this model, our universe is a three-dimensional brane floating in a higher-dimensional space. The collision of our brane with another causes the universe to contract, while the rebound from this collision leads to a new expansion phase. The cyclic model is an extension of the ekpyrotic model, proposing that these brane collisions happen periodically, leading to an infinite series of bounces. Unlike the standard Big Bang model, which implies a singular origin, the cyclic model posits that the universe has no true beginning or end. It simply goes through eternal cycles of birth, death, and rebirth. While bouncing cosmologies offer an elegant solution to some of the problems associated with the Big Bang theory, they are not without their challenges. One of the primary difficulties lies in explaining the observed properties of the universe, such as its homogeneity, isotropy, and the CMB. In the standard model, these properties are explained by the theory of cosmic inflation, which proposes that the universe underwent a rapid expansion shortly after the Big Bang. This inflationary phase smooths out any irregularities and creates the uniform cosmos we observe today. Bouncing cosmologies must find alternative explanations for these properties, often requiring fine-tuning of the model parameters. Another challenge is the lack of direct observational evidence for a bouncing universe. While some aspects of these models may leave imprints in the CMB or the distribution of large-scale structures in the universe, these signatures are subtle and difficult to distinguish from those predicted by the standard model. Despite these challenges, bouncing cosmologies have profound implications for our understanding of the universe. If the universe is indeed cyclical, it suggests that the cosmos is far older and more complex than we currently believe. The notion of an eternal universe, with no true beginning or end, challenges our perceptions of time and existence, forcing us to rethink our place in the cosmos. As our understanding of the universe continues to evolve, bouncing cosmologies remain a tantalizing possibility. Future advancements in quantum gravity, observational cosmology, and theoretical physics may provide the tools needed to test these ideas and determine whether our universe is truly cyclic. For now, the bouncing universe remains a compelling alternative to the standard model, offering a vision of the cosmos that is as enigmatic as it is eternal. Whether or not this vision reflects reality, it serves as a powerful reminder of the limits of our knowledge and the endless possibilities that lie beyond the horizon of our understanding. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Mercury should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference of nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. A thin atmosphere, a magnetic field, and a stash of volatile compounds still persist on Mercury, features that scientists usually associate with planets that are larger and farther away from the Sun. While new observations from the last few decades have given scientists good cause to revise their opinion of Mercury.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?
Its secrets remain. But now, by using powerful telescopes, scientists have stumbled upon these secrets. But what they found is so weird. There is something moving that they never saw anywhere else. Such a stunning revelation could even lead to crucial missions to reveal a terrifying truth about our universe. Join us as we shed light on the dark shadow that Mercury has kept under wraps. Named for the fleet-footed Roman messenger god, Mercury is the closest planet to the Sun, zipping around our parent star at an average of 36 million miles away. However, Mercury's orbit is not a perfect circle. The planet can pass as close as 29 million miles and as far away as 43 million miles. Living up to its name, Mercury is the fastest planet in the solar system, speeding along at about 29 miles per second and completing each orbit around the Sun in just 88 Earth days. Mercury is also the smallest planet in the solar system, measuring just 3,032 miles wide at its equator. That makes it only slightly larger than Earth's moon. Because Mercury is so small and so close to the Sun, it is the most elusive of the 5 planets that are visible to the naked eye. You can only catch Mercury at dawn and dusk, and it usually does not rise far above the horizon. But that's not the only time the tiny planet makes an appearance. Because of its position in the solar system, Mercury passes between Earth and the Sun 13 times each century, in an event known as a transit. During a transit of Mercury, observers on Earth can see the planet in silhouette as it seems to sweep across the Sun's disk. Since ancient times, people observing the heavens have noticed that the naked eye planets sometimes appear to move backward, briefly shifting from their usual eastward motion to a westward path across the sky. This retrograde motion is an illusion created when one planet moves faster in its orbit than another, so that it catches up to and passes the slower world. For observers on Earth, Mercury is in retrograde about 3 to 4 times a year. If you could watch the skies from the surface of Mercury, you would sometimes catch the rare sight of the Sun in retrograde. As Mercury makes its closest approach to our smoldering star, its orbital speed exceeds its rate of rotation on its axis. That means someone standing on Mercury would see the sun start to rise, then briefly set, then rise again, all within the same day. Like the other planets in the solar system, Mercury was born about 4.5 billion years ago, condensing from the swirling ring of dust and gas left over from the sun's formation. The small planet cooled very quickly, contracting enough within the first billion or so years to prevent magma from escaping through the outer crust and ending geologic activity such as volcanism on the surface. And while Mercury may be small, it's hefty. Although its diameter is barely larger than the Moon's, Mercury is over 4 times as massive as Earth's natural satellite. In fact, Mercury is the second densest planet in our solar system, after Earth. The planet's extreme density comes from the fact that it has a large iron core that makes up about 60% of the planet's volume. In contrast, Earth's core by volume is only about 15%. The abnormal internal structure has spawned several theories on Mercury's birth. Scientists think that perhaps early Mercury's outer layer was boiled away by the sun or scattered by solar winds. Or perhaps the young planet could have been struck by a large impactor that stripped away most of the softer outer layer, leaving behind its sturdier heart. Since part of the mantle and crust are still present today, this suggests that the collision may not have been a head-on smack, but a glancing brush that preserved some of Mercury's original layers. The first mission to Mercury, Mariner 10, was launched in 1973 and found that Mercury still sustains a magnetic field. The discovery came as a shock to the scientific community, who had assumed that such a small planet would have rapidly cooled, and its insides would have congealed, thereby losing any means of magnetism at the global scale. The presence of a magnetosphere implies that part of Mercury's core is still churning. Mercury's magnetic field is about 100 times weaker than Earth's on their respective planetary surfaces. The sluggish dynamo means that the planet is at the tail end of its developmental stage, on its way to becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, documented that the planet's magnetic field is off-kilter. The magnetic South Pole doesn't sit on the geographic South Pole. Instead, it is buried almost at the center of the planet. The magnetic field offers a glimpse of the planet's interior and a snapshot of its history, hinting at how far the whirling insides have decelerated over billions of years. Due to its proximity to our star, Mercury is hot. If we're being quantitative, it's actually extremely hot. As the closest planet to the Sun, it completes an orbit in just 88 Earth days, achieving a maximum temperature during the day of a whopping 427 degrees at its hottest equatorial locations. Mercury rotates very slowly, so its night side spends a consecutively long time in the dark, shielded from the sun. During those times, it gets down to just minus 173 degrees. That low temperature is incredibly cold, and far colder than any known naturally occurring temperatures here on Earth. But despite being the closest planet to the Sun, Mercury is not the hottest planet in the solar system. Venus is about twice as far from the Sun on average as Mercury is, taking about 225 Earth days to orbit the Sun. It also rotates even slower than Mercury, spending more than 100 consecutive Earth days at a time bathed in sunlight, and then an equal amount of time in darkness. And yet, when you measure the temperature of Venus, there's a surprise. Venus is the same temperature at all times, day or night, at an average of 462 degrees, making it even hotter than Mercury. This strange occurrence did more than just puzzle astronomers when they first discovered it. It mortified them. Venus wasn't large enough to generate its own heat, and yet it was hotter at Venusian midnight than at Mercurian high noon. Why is that? Well, that is because of the main difference between the two worlds. Venus has a very substantial one that's some 190 times as thick as Earth's is, but Mercury, instead of a substantial atmosphere, has such a thin atmosphere that it doesn't really qualify as an atmosphere. Instead, scientists call this wispy layer of gas an exosphere, where the gas is so rarefied that it hardly registers a pressure reading. Mercury takes a constant beating from the sun, so its exosphere has to regenerate itself from the surface. Since the 1980s, astronomers have detected in Mercury's exosphere atomic sodium, potassium, and calcium, metals with strong emission signals that can be observed all the way from Earth with telescopes. These metallic elements are not usually thought of as gases, but they find their way into Mercury's skies by dint of solar particles and meteorites striking the planet's surface. Solar winds gouge the resulting exosphere, and the interactions between the gases and sun-flung particles fashion a 15-million-mile-long glowing tail behind Mercury. This tail lengthens and shrinks seasonally, depending on Mercury's proximity to the sun. If you were standing on Mercury and looking up at the right time of the year, Mercury's long tail would appear in the sky as a faint orange glow, as if the heavens were illuminated by sodium streetlights. A planet perched right at the sun's maw shouldn't harbor any water, let alone ice, or so researchers thought. But in the 1990s, scientists at Goldstone in California and the Arecibo radio telescope in Puerto Rico directed a stream of radar signals toward Mercury. The teams were astonished to observe two brightly reflective spots at the poles, likely icy deposits. In 2012, Messenger confirmed that the ice at Mercury's North Pole was frozen water. Laser measurements on board identified carbon-rich material on the surface that insulates an ice pack underneath. Mercury has managed to cling on to its water because it has pockets in permanent shadow. Relative to its orbit around the sun, the planet spins perfectly upright, like a soldier at attention facing a commanding officer. That means the impact craters near the poles have insides that never see any daylight. Temperatures within these divots dip below minus 173 degrees Celsius, close to the temperature where nitrogen gas liquefies. It's cold enough that ice can be stable over geological timeframes. And as on most other rocky planets, the water on Mercury probably came from asteroids that crash-landed onto the surface. This water hides in Mercury's craters, untampered with since primordial times. On other terrestrial planets in the solar system, geological processes such as weather cycling have scattered the externally delivered water all around the globe. If scientists want to sample ancient ice in its pristine form in the solar system, the best source is probably Mercury's poles. Mercury defied expectations again when Messenger detected volatiles on the sun-scorched world. Volatiles are chemicals that can jump between solid and gas phases in a short temperature change. Mercury already proved it sheltered water, a volatile, but Messenger found others such as sulfur, potassium, and chlorine that easily vaporize at moderately high temperatures. These volatiles are distributed all across the surface of the planet. For its size, Mercury contains as much volatile content as other terrestrial planets in the solar system that are farther from the sun and hence much colder. Where the volatiles come from and how Mercury has retained them are still matters of scientific debate. Some researchers think that the volatiles came from underground relatively recently, while others think the chemicals have persisted on the surface since an embryonic Mercury condensed from its protoplanetary disk. The volatiles on Mercury raise questions. For example, if planets that edge up against their stars have volatiles, especially water, could these locales also be habitable? Well, it's possible that Mercury once held the ingredients for life. Indeed, Mercury has irregular depressions in the ground called hollows. Mariner 10 first glimpsed them in 1975. Then, Messenger photographed these shallow tracts at fine resolution. The depressions span from a few dozen feet to over a mile across, and they may be as deep as 120 feet. They look like the soft, airy insides of a sourdough loaf cut open. The hollows may be the doing of volatiles, scientists theorize. Since the atmosphereless Mercury has no rain or wind to carve the land, surface features like hollows can only be formed from other processes, such as the ground leaking volatiles into space. Hollows are relatively young formations, about 100,000 years old on average, compared with some 4 billion-year-old impact craters on Mercury. Scientists think hollows are still forming today, and hollows are unique to Mercury. No other celestial body in the solar system seems to present similar pockmarks. In recent years, scientists have identified other structural formations on Mercury: chaotic terrains, jumbled ridges that look like a failed game of Jenga, cut up vast swaths of the land. Some researchers think the chaotic terrains are the result of the ground wafting volatiles until it loses structural integrity and collapses. Other scientists think that chaotic terrains form after ripples from an asteroid impact encircle the planet and meet on the opposite side of the globe. In addition, Mercury's topography also provides clues that volcanoes once spewed lava on the planet. Mariner 10, first glimpsed and then Messenger later confirmed that glossy plains spread across Mercury's surface. Each plain suggests pooled lava smoothed over older craters and ridges. Researchers think that magmatic volcanism halted on Mercury anywhere between 1 billion to 3.5 billion years ago, due to planetary cooling and contraction that plugged up the magma's escape routes. Mercury has also shown signs of another kind of volcanism: explosions. If streaming lava is like a runny nose, then explosions are the volcanic equivalent of a sneeze. Irregular pits several miles across and more than 2 miles deep hint at ancient pyroclastic volcanoes that self-destructed. Scattered around these pits are deposits that researchers think are ejecta from the explosion. These types of volcanic bursts are probably caused by volatiles underground. When these buried chemicals rise to the surface, they expand in volume. Eventually, the pressure buildup of gases causes the volcano to pop, like an overfilled balloon. But volatiles, a chemical category that includes water, are essential for sparking and supporting life as we know it here on Earth. So, their potential presence on Mercury is an intriguing development. Astronomers now speculate that beneath the scorching surface of Mercury, the closest dwarf planet to the Sun, there could be signs of life. But how could volatiles, which are essential to life here on Earth, survive on a planet whose daytime temperatures soar to 430 degrees Celsius and drop to minus 180 degrees Celsius at night? Alexis P. Rodriguez, a researcher at the Planetary Science Institute in Arizona, explained that while the planet's surface swings wildly between temperature extremes, just below the surface, temperatures are milder. In the words of Rodriguez, it's likely that there was some sort of water that formed in part of Mercury's crust, but the team cannot yet tell exactly what volatiles were present when the planet's surface broke apart. While the mystery remains, a completely unexpected discovery made by NASA's Messenger spacecraft revealed that a 10-mile-thick diamond mantle may lie beneath the crust of Mercury. While instances of such valuable encrustation might sound tantalizing, turning these precious stones into fashionable jewelry remains an impossibility due to their inaccessible location deep within the planet. However, these gems could hold the key to unraveling some of the big unanswered questions circling around Mercury composition and its rather curious magnetic field. These diamonds may facilitate heat transfer between the core and mantle, thereby creating temperature differences and causing liquid iron to circulate, a process that would kickstart the creation of a magnetic field. The discovery of a potential diamond layer within Mercury opens new avenues for planetary research and composition studies, not only of Mercury, but also of other celestial bodies. Understanding the unique geological characteristics of Mercury could provide deeper insight into the formation and evolution of the solar system. The new discovery also prompts a reconsideration of the processes involved in planetary formation. Diamonds are typically associated with high-pressure environments, suggesting that similar conditions may exist in other distant rocky exoplanets and moons within our solar system. Studying extreme planetary conditions can reveal not only the composition of these bodies, but also the historical processes that formed them, leading to a more comprehensive understanding of geology across the cosmos. The potential discovery casts a new light on the evolution of carbon-rich exoplanets. The process that led to the formation of a diamond layer on Mercury could also be at play on other planets, possibly leaving similar traces. The arrival of the Bepi-Colombo spacecraft, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, in 2025 will provide better opportunities to delve deeper into this intriguing discovery. Bepi-Colombo was launched in 2018 on a complex trajectory to the solar system's innermost planet. The ESA reports that the spacecraft's thrusters have lost some power. Bepi-Colombo's mission is to complete a comprehensive investigation of Mercury's magnetosphere, magnetic field, and internal and external structure. But traveling around in the inner solar system is complicated, and the Bepi-Colombo spacecraft will use more energy getting to Mercury than it takes to get to Pluto. The spacecraft will perform 9 planetary flybys before reaching its destination at the end of 2025. Bepi-Colombo has already performed 1 gravity assist at Earth, 2 at Venus, and 5 at Mercury. It'll perform 1 more at Mercury in January 2025. The Mercury Transfer Module, or MTM, is the part of the spacecraft that delivers a pair of orbiters to Mercury. On April 26th, as the spacecraft was about to execute its next maneuver, the MTM didn't deliver enough electrical power to its thrusters. A team working on it restored the thrust back to 90% on May 7th. But the MTM still isn't deliver enough electricity to get back to 100% thrust. Despite the power problems, the spacecraft is on track to complete its final Mercury flyby. A team is working to maintain the current power level and to understand how the diminished thrust will affect future maneuvers. They're also working on restoring full power to the thrusters. To facilitate this, the mission's flight control team at the European Space Operations Center in Darmstadt, Germany, has arranged additional ground station passes. Bepi-Colombo employs a solar electric propulsion system. 2 15-meter-long solar cells gather energy and deliver it to 4 ion thrusters that use xenon propellant. The thrusters are mounted on gimbals, making them aimable. Bepi-Colombo consists of 3 separate spacecraft. The Mercury Transfer Module is kind of like a tugboat, delivering 2 separate orbiters to Mercury. One of the orbiters is the Mercury Planetary Orbiter, and it carries 11 scientific instruments, including cameras, several spectrometers, a magnetometer, and others. The other one is the Mercury Magnetospheric Orbiter, largely built by JAXA. It carries 5 groups of instruments, including one group that will study the plasma and neutral particles from the planet, its magnetosphere, and the solar wind. While waiting for the first data obtained by Bepi-Colombo, scientists also put their hope in another tool, the James Webb Space Telescope. The Supreme Space Telescope comes with significant advantages over any previous mission. First and foremost is its size. James Webb features a 21.7-foot mirror composed of 18 gold-plated hexagonal segments. This colossus gathers more than 6 times as much light as the Hubble Space Telescope's 7.8-foot mirror, so it can record light from objects 6 times faster than its predecessor. But Webb's sensitivity to infrared light is the real game-changer. The Space Telescope can view wavelengths from the red end of the visible spectrum to the mid-infrared. Hubble's optics are optimized to record radiation from the ultraviolet to the near-infrared, with the majority of its sensitivity centered on visible light. Perhaps surprisingly, in its intended infrared domain, James Webb generally won't resolve finer details than Hubble achieves in optical light. Although resolution increases with mirror size, it also diminishes with wavelength. Observing in the infrared allows astronomers to see galaxies that existed less than 1 billion years after the Big Bang. These distant objects emit ultraviolet and visible light, but the expansion of the universe shifts this radiation to longer infrared wavelengths. Peering into the infrared is the only way to observe these young galaxies from Earth's vicinity. The same holds true for newly forming stars. The dust that envelops infant suns scatters visible light, hiding what lies within from our eyes, but it lets infrared radiation largely pass through. Despite its focus on distant galaxies and star formation, James Webb is an all-purpose observatory. Its powerful infrared eye sees details in solar system objects beyond the reach of conventional telescopes. Early observations include studying cloud belts on the gas and ice giant planets, tracking cloud formations on Saturn's largest moon, Titan, exploring Pluto's climate, and probing many of the smaller asteroids and trans-Neptunian objects that populate the outer solar system. The telescope even observed the asteroid moonlet Dimorphos in September, when NASA's double asteroid redirection test slammed into it. The impact slightly changed the object's orbit around its parent body, Didymos, helping the space agency assess its ability to alter the course of potentially hazardous asteroids that could cross Earth's path. Thus, it's not far-fetched to think of the Space Observatory can take a closer look at Mercury, unlocking the subterranean secrets of the closest planet to the Sun. In the latest observation, using James Webb, astronomers discovered that Ariel, a moon of Uranus, could be hiding in a buried liquid water ocean. The discovery could supply an answer to a mystery surrounding this Uranian moon that has perplexed scientists. The fact Ariel's surface is covered with a significant amount of carbon dioxide ice. This is puzzling, because at the distance, Uranus and its moons exist from the Sun, 20 times further out from the Sun than Earth. Carbon dioxide turns to gas and is lost to space. This means some process must refresh the carbon dioxide at the surface of Ariel. Previous theories have suggested this happens as a result of interactions between Ariel's surface and charged particles trapped in Uranus's magnetosphere that provide ionizing radiation, breaking down molecules and leaving carbon dioxide, a process called radiolysis. However, new evidence from the Webb telescope suggests the source of this carbon dioxide could come not from outside Ariel, but from its interior, possibly from a buried subsurface ocean. Because chemical elements and molecules absorb and emit light at characteristic wavelengths, they leave individual fingerprints on spectra. The team behind this discovery used James Webb to gather spectra of light from Ariel, which helped them paint a picture of the chemical makeup of the Uranian moon. Comparing this to simulated spectra from a chemical mix in the lab here on Earth revealed to the team that Ariel has some of the most carbon dioxide-rich deposits in the solar system. Not only did this add an extra 0.4 inches of thickness to the ice on the side of the tidally locked Ariel that permanently faces away from Uranus, but it also revealed clear deposits of carbon monoxide for the first time. As team leader Richard Cartwright from the Johns Hopkins Applied Physics Laboratory, or APL, said in a statement, "It just shouldn't be there. You've got to get down to 30 kelvins, minus 405 degrees Fahrenheit, before carbon monoxide's stable. The carbon monoxide would have to be actively replenished, no question." That's because Ariel's surface temperature is, on average, around 18 degrees Celsius warmer than this key temperature. Cartwright acknowledges that radiolysis could account for some of this replenishment. However, observations from Voyager 2's 1986 flyby of Uranus and its moons and other recent findings have suggested that the interactions behind radiolysis could be limited because Uranus's magnetic field axis and the orbital plane of its moons are offset from each other by about 58 degrees. That means that the majority of the carbon-oxygen compounds seen on Ariel's surface could be created by chemical processes in a liquid water ocean trapped under ice on Ariel. Once created in the seep water ocean of Ariel, these carbon oxides could then escape through cracks in the icy shell of the Uranian moon, or could even be explosively ejected by powerful eruptive plumes. Scientists have suspected for some time that the cracked and scarred surface of Ariel may indicate the presence of active cryovolcanoes, volcanoes that erupt plumes of icy slush rather than lava. These plumes could be so powerful that they launch material into Uranus's magnetic field. The majority of the cracks and grooves seen on the surface of Ariel are located on the side of the moon that faces away from Uranus. If carbon dioxide and carbon monoxide are leaking from these features to the surface of the Uranian moon, this could explain why these compounds are found in greater abundance on this trailing side of the icy body. In addition, James Webb also picked up more chemical evidence of a subsurface liquid water ocean. Spectral analysis hinted at the presence of carbonate minerals, salts created when rock meets and interacts with liquid water. As Cartwright explained, if our interpretation of that carbonate feature is correct, then that is a pretty big result because it means it had to form in the interior. That's something we absolutely need to confirm, either through future observations, modeling, or some combination of techniques. Uranus and its moons haven't been visited by a spacecraft since Voyager 2 almost 4 decades ago, and this wasn't even the spacecraft's primary mission. In 2023, the Planetary Science and Astrobiology Decadal Survey emphasized the need to prioritize a dedicated mission to the Uranian system. Cartwright believes such a mission would present an opportunity to collect valuable information about Uranus and Neptune, the solar system's other ice giant. Such a mission could also deliver vital data about the other potentially ocean-bearing moons of these systems. This information could then be applied to extrasolar planets or exoplanets beyond the solar system. As team member and NASA Applied Physics Laboratory scientist Ian Cohen said, all these new insights underscore how compelling the Uranian system is, whether it's to unlock the keys to how the solar system formed, better understand the planet's complex magnetosphere, or determine whether these moons are potential ocean worlds. Many of us in the planetary science community are really looking forward to a future mission to explore Uranus. In another remarkable study made by James Webb, astronomers have investigated a new super-Jupiter planet that is one of the coldest worlds ever seen outside the solar system. The exoplanet is located in the triple star system Epsilon Indi, which sits around 12 light-years away. The planet is designated Eps Ind Ab and has a mass around 6 times that of Jupiter. It orbits its red dwarf parent star at a distance similar to that between Neptune and the Sun. This gives the world a surface temperature of around 0 degrees Celsius and means one orbit of the planet takes around 200 Earth years. The Webb telescope was able to image the exoplanet using the sensitive infrared capabilities of the mid-infrared instrument. The investigation of Eps Ind Ab could help astronomers better understand the evolution of gas giant planets and their systems. This is the first time that the powerful space telescope has been able to image an exoplanet that wasn't previously imaged from the ground. Eps Ind Ab is also the coldest exoplanet James Webb has been able to study thus far. That's why scientists were excited when we realized we had imaged this new planet. To their surprise, the bright spot that appeared in our MIRI images did not match the position we were expecting for the planet. They added that previous studies had correctly identified a planet in this system, but had underestimated the super-Jupiter gas giant's mass and orbital separation. The team was able to correct this with the help of James Webb. The crew determined the planet has a highly elliptical, or flattened, orbit that, at its closest, brings it to a distance about 20 times the distance between Earth and the Sun. At the furthest point in its orbit, Eps Ind Ab is 50 times further away from its parent star than the average distance between Earth and the Sun. The world's parent star, a red dwarf named Eps Ind A, has 2 stellar companions. Both are brown dwarfs, or failed stars, named as such because they're objects that form like stars, but can't gather enough mass to trigger nuclear fusion processes in their core that define what a main sequence star is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?